Hey there, Math 126 students. Somebody in office hours asked me this. They found this rather challenging question from the fall 2022 final. It's right at the end of the exam. I suspect the instructors were experimenting with how students would do, so I suspect this was really meant as a major challenge. So if you got stuck here, then you're probably like many other people. But I want to talk about some pieces we can take away from this, and somebody's asking me something about it on the discussion board, and I'll show you some visuals. I'm not going to go all the way through all the details. I just wanted to say a few things that are, of general interest to us. The question talks about, it says, find a normal vector to the tangent plane at the point here, at some unknown point. So a comment is the tangent plane formula looks like this. And typically you put numbers in these spots. So hopefully we know that pretty well. You need to compute the partial derivatives to find those, all that stuff. Now we did it when we were finding this. We talked about how that was the simplified formula. We talked about how this is an upward pointing normal, meaning if you move these things to the other side, you get a number here, and a 1. And that's an upward pointing normal. So here's a visual of this. We didn't do very much with this. You do a bit of this in the next course if you take Math 224. That purple vector is pointing upward and out of the surface. So occasionally there's a need for that. And in this case, we actually know what those things are. So we don't know what X and Y are. That's a hard piece of the puzzle. But the question is actually, let me get this visual out. The question is asking about this plane. And the part that's interesting is it's asking if you're restricted to that little tiny square on the bottom there. I actually drew just the surface above that square, which is that. Let me get rid of this for a second. So there's the surface only above the square, which is super weird there. The question is, what angle does that make with the ground? Now, sometimes that angle it makes with the ground is big. It's like if you get towards the top, the angle it makes with the ground is actually going to be small. And then if you actually could see this as we're doing now, you can see that the closer and closer you get. So the place that's going to have the largest angle is going to be way down at the edge there at the bottom. So I think that's when, yeah. So if you could see the visual, the answer is at a corner. Just because I can see it. Like that's by far the steepest tangent plane you can have. And so I know the answer is when X is 2 and Y is -2. I think there's a similar one on the other side. Over here. That's the answer. So it ultimately is a global max question, but there's a lot that goes into sort of unpacking that. Okay, so let's just extract a few things. So from the first part, we would say, all right, let's put our derivatives in here. And I think in the solutions, they did the downward pointing normal, which is also fine. But if I plop this in here, I'm going to have negative. And this will be -2 x0 plus y0. And then I'm going to have -2 y0 plus x0, comma 1. So that's what we're going to use in the next part. I think that's why they did part A. So part B says, I want to maximize the angle between these two planes. The plane, the XY plane, which would have a normal pointing straight up, and this other plane, which I don't even know. So this was the challenge. The guiding principle here is, what are we optimizing? We're optimizing the angle, and it's between these. And like I said, this is I suspect very few students made progress on this. It must have been an intentional extreme challenge. Again, everyone faced the same challenge, but this does not mean lose sleep over this and only study this. Know the other things. But in this case, the angle, so this is an important formula, the angle between two vectors. The dot product is just 1. The magnitude of the first vector is this. So you just get this magnitude. So you do boil it down to the following. So we are trying to optimize this. At this point, if you want to just switch to writing x and y, that's fine. I have it down to a 2-variable function. I probably shouldn't use f because we already are using that for something else. So I want to optimize that 2-variable function over this square. So we do have a plan. It's just kind of it took a lot to get there. So you would see if it has any critical points inside the region. Now, you can use this same trick of when you go to take derivatives. I skipped over something here. In order to make cosine in order to make the theta as large as possible, you need this to be as small as possible. And so you need this to be as large as possible. I am going to switch over. So I mostly just wanted to say kind of the piece we were saying there, but I also am going to pull up the solution so you can see the magnitude of some of the challenges, but I hope I've at least boiled down some pieces. So in the solutions here, sorry, I'm having trouble fitting it in the screen. And this is not something I normally do, but I know people are asking about this. Okay, so they make this, let's kind of just read through these solutions and make a few notes and then call it a day on this one. The largest possible acute angle means the smallest possible positive cosine of this. Cosine is bigger the closer you get to 0. So that's what they're saying. So the bigger the angle is, the closer you get to 90 degrees. The smaller sine wave. We're trying to find the largest possible angle. So we're trying to get the value of this that's closest to 0. Okay, so we're trying to get this as close to 0 as possible. All right, so that took a little bit. I mean, that's in itself a bit of thinking to try to simplify it. You could just write arc cosine of both sides and take the derivatives. So this stuff that we're doing here in this solution is trying to make it easier to do the derivatives. But you could say theta equals arc cosine of this 1 over this mess I have here, and then just start doing the analysis. So all of this discussion was trying to save us from doing that. And they even did another trick, which is they squared both sides and said that the maximum of this will occur when the inside is maximum. So they did several bits of simplification that I'm curious how many students knew or figured that piece out. Again, this probably was an extreme challenge. Okay, so at this point we can find the critical points of that. You don't have to expand, but the critical point is only just one critical point. It's at 0, 0, and you plug it in and you get a really large. You don't get a at 0, 0. You're actually at the peak on this thing. Are we at the peak? Maybe. Okay, so then you start doing the boundaries. X equals 2. X equals -2, and the boundaries, because we're talking about this square, y equals -2, y equals 2. So that's what's happening at the end of these solutions. Again, it's a big problem. You plug in a 2 here. They had already expanded. Then you take the derivatives, you look at the endpoints. After all that's done, it does end up being 2 of the endpoints as we saw in the visual. So I'm just going to leave that as that. Yes, it's pretty extreme challenge, but I hope that at least tells you what it was about. Ultimately, you had to think about, so the things to take away from this. If we have a tangent plane, we also have a normal vector pointing out of it. We can get that. If we're maximizing an angle, we would write the angle. The rest of this just was kind of a lot of challenges in one problem. All right, I hope that answers that question.